Welcome to Triune Biblical University Global Extension USA channel. A warm welcome to all our returning subscribers and a heartfelt greeting to our new viewers. We're so glad to have you with us today. Whether you've been following us for a while or are just joining the community, we're excited to embark on this learning journey together. At Triune Biblical University Global Extension USA, we strive to provide valuable educational content that empowers you to grow, learn, and succeed. Your continued support and participation mean the world to us. In today's session, we are diving into lecture topic, where we'll explore important concepts and provide practical knowledge that you can apply in real-world scenarios. This lecture is designed to challenge your thinking and deepen your understanding, whether you're a beginner or an advanced learner. Thank you for joining us, and we hope you find today's lecture both insightful and inspiring. Let's get started. Chapter 6: Slope Stability and Landslides. 6.1 Slope Stability Analysis Methods. Slope stability analysis is a crucial aspect of geotechnical engineering, as it helps in evaluating the safety of slopes and the potential risks of landslides. Understanding the factors that influence slope stability is essential for designing safe structures, roadways, and embankments, as well as for mitigating the risks posed by natural hazards. Various methods have been developed to assess the stability of slopes under direct conditions, including static and dynamic loading, soil properties, and environmental factors. In this section, we explore several widely used methods for analyzing slope stability, from traditional analytical approaches to more advanced numerical techniques. 6.1.1 Limit Equilibrium Method, LEM. The limit equilibrium method is one of the most widely used techniques for assessing slope stability. This method involves analyzing the forces acting on a potential sliding mass and determining the equilibrium condition at the point of failure. Key features. Assumptions. The soil is considered to be a rigid, non-deformable body, and the failure surface is assumed to be a potential slip surface, typically circular or planar. In shape. Force equilibrium. The method calculates the forces acting on a failure mass, including the driving forces, e.g., gravity, water pressure, and resisting forces, e.g., shear strength of the soil. The ratio of resisting to driving forces determines the factor of safety, Fs, of the slope. Factor of safety, FSFS, is calculated as the ratio of the resisting forces to the driving forces. A factor of safety greater than 1.0 indicates stability, while a value less than 1.0 indicates potential instability. Applications. Simple and effective for slopes with well-defined failure surfaces. Commonly used in preliminary design or when complex site conditions are not present. Types of limit equilibrium methods. Method of slices, e.g., Janbu, Bishop, and Fellinius methods. These methods divide the potential sliding mass into vertical slices and solve equilibrium equations. For each slice, the key difference between the methods lies in how forces are assumed to act within each slice. Bishop's simplified method, a commonly used method due to its simplicity and ability to account for non-circular slipped surfaces. The Linnaeus method, ordinary method of slices, a simplified approach that assumes no interslice forces, making it less accurate for slopes with complex geometry. 6.1.2 Finite Element Method, FEM. The finite element method, FEM, is a more advanced numerical approach that divides the slope into smaller, discrete elements, allowing for a detailed analysis of the entire slope system, including its geometry, material properties, and boundary conditions. FEM is especially useful for complex slope conditions where traditional methods, like LEM, may not provide accurate results. Key features: continuous approach. Unlike LEM, which focuses on force equilibrium, FEM solves the equations of motion for the entire slope, accounting for deformations, stresses, and strains within the material. Soil heterogeneity. FEM can model heterogeneous soils with varying material properties, making it suitable for more complex site conditions, such as layered soils or varying water tables. Stress-strain behavior. FEM can consider the nonlinear, stress-dependent behavior of soil, allowing for a more realistic representation of material behavior under loading conditions. Applications: suitable for complex slopes with irregular geometries or material properties. Used in situations where detailed analysis of deformation, stress, and strain is required, such as in cases involving large infrastructure or critical slopes. Advantages: provides a more detailed, comprehensive view of slope behavior, can account for large deformations and nonlinear material properties. 6.1.3 Finite Difference Method, FDM. The finite difference method, FDM, is another numerical technique for analyzing slope stability that divides the slope into a grid of nodes, solving the differential equations that govern the equilibrium conditions for each node in the system. FDM is particularly useful for modeling the behavior of slopes under dynamic loading conditions, such as seismic activity or rapid changes in pore water pressure. Key features: discretization. The slope is divided into a grid of points, and the equations of motion are solved for each point using finite differences. Dynamic analysis. FDM is particularly useful for time-dependent analyses, such as assessing the impact of earthquakes or rapid rainfall infiltration on slope stability. Soil structure interaction. FDM can model the interaction between the soil and structures, such as retaining walls or foundations, in the context of slope stability. Applications: used for time-dependent or dynamic analysis of slope stability. suitable for cases involving rapidly changing conditions, such as heavy rainfall, seismic loading, or sudden changes in pore water pressure. Advantages: useful for analyzing dynamic and time-dependent problems. Can model complex geometries and boundary conditions. 6.1.4 Strength Reduction Method, SRM. The strength reduction method, SRM, is a popular technique used to assess the factor of safety and slope stability analysis by progressively reducing the shear strength of the soil until failure occurs. The factor of safety is determined based on the point at which the shear strength is reduced to a level where the slope fails. Key features: progressive reduction. SRM involves reducing the soil shear strength, either cohesion or friction, incrementally, and monitoring when the slope reaches failure. This method directly evaluates the strength of the slope and does not rely on pre-defined failure surfaces. Nonlinear analysis. SRM can account for the nonlinear behavior of soil, which is particularly useful for soils that exhibit stress-dependent strength behavior. Applications: typically used in conjunction with numerical methods like FEM or FDM. Effective for complex slopes where traditional methods like the limit equilibrium method are difficult to apply. Advantages: provides a direct evaluation of the strength of the slope. Can handle complex, nonlinear material behavior and geometries. 6.1.5 Numerical slope stability methods. In addition to the methods mentioned above, several other numerical techniques are commonly used to evaluate slope stability. These include boundary element method, BEM. This method focuses on solving boundary value problems and is particularly useful for analyzing slopes with complex geometries or irregular boundaries. Particle flow code, PFC. PFC simulates the behavior of granular materials by modeling the interaction between individual particles, making it suitable for analyzing soil behavior under loading. Applications: used when other methods are inadequate for complex slope conditions or when more detailed, particle-based modeling is necessary. Advantages: highly flexible and can model complex material behavior and geometries. 6.1.6 Empirical methods. In some cases, empirical methods may be used to estimate slope stability, especially in situations where detailed data or complex analysis is not available. These methods are often based on historical data or simplified assumptions. Key features: simplified assumptions. Empirical methods typically rely on generalizations or historical experience to predict slope behavior. For example, the safety factor may be determined using guidelines from past landslide occurrences in similar conditions. Quick estimations. These methods provide a rapid, rough estimation of slope stability, which can be useful for preliminary assessments. Applications: used for preliminary design or when detailed site data is unavailable. Common in projects with minimal risk or where other methods are not feasible. Advantages: fast and simple, providing initial estimates for slope stability. 6.1.7 Conclusion: the selection of an appropriate slope stability analysis method depends on the complexity of the slope, the available data, and the specific project requirements. While traditional methods like the limit equilibrium method owe a simple and effective approach for many situations, more advanced numerical techniques such as FIM, FTM, and SRM are required for analyzing complex, heterogeneous slopes or dynamic loading conditions. Empirical methods can serve as useful tools for quick estimations or preliminary assessments. By carefully considering the factors influencing slope behavior, engineers can choose the most appropriate method to ensure the stability and safety of slopes in various applications. Chapter 6: Slope Stability and Landslides. 6.2 Factors affecting slope stability. Slope stability is a critical concern in geotechnical engineering, especially in areas prone to landslides, erosion, or other types of ground failure. Various factors influence the stability of slopes, and a comprehensive understanding of these factors is essential for designing safe and stable slopes, embankments, and structures. In this section, we explore the key factors that affect slope stability, which include geological, hydrological, and environmental aspects, as well as human activities. 6.2.1 Soil Properties. Soil properties play a fundamental role in determining the stability of a slope. The characteristics of the soil or rock that make up the slope directly influence its ability to resist failure. Key soil properties. Shear strength. The shear strength of soil is one of the most significant factors affecting slope stability. Shear strength is a function of the soil's cohesion and internal friction angle. Soils with low shear strength are more prone to sliding, while soils with high shear strength provide greater stability. Cohesion. See, cohesion refers to the internal forces that bind soil particles together. Higher cohesion in cohesive soils, e.g., clay, improves slope stability as the soil resists sliding and deformation. Angle of internal friction. The angle of internal friction represents the resistance to sliding between particles in granular soils, e.g., sand and gravel. Higher angles of internal friction contribute to greater stability. Unit weight of soil. Gamma. The unit weight of soil influences the weight of the soil mass, which acts as a driving force in slope failure. Heavier soils with higher unit weight can increase the likelihood of failure under steep slope conditions. Soil type and composition. Diorite soil types, such as sandy soils, siltous soils, or clayey soils, behave deerrantly under stress. granular soils tend to be more stable due to their ability to drain water easily, while cohesive soils may experience increased pore water pressures that weaken their shear strength. 6.2.2 Water content and pore pressure. Water plays a significant role in the stability of slopes by altering the stress conditions within the soil mass. The presence of water affects soil behavior in several ways, especially in the form of pore water pressure, which can weaken the soil's shear strength. Key hydrological factors: rainfall and water infiltration. Heavy rainfall or prolonged precipitation can lead to increased water infiltration into the slope, raising the pore water pressure and reducing soil strength. Saturated soils, particularly clays, become more susceptible to sliding as their shear strength diminishes when excess pore pressure is generated. Groundwater table. The location and variation of the groundwater table can significantly influence slope stability. If the groundwater level is near the surface or fluctuates with the seasons, it can increase the likelihood of slope failure, especially in fine-grained soils. Pore water pressure. Pore water pressure is the pressure exerted by water within the voids of the soil. High pore water pressure can reduce the active stress within the soil, decreasing shear strength and potentially leading to slope failure. Capillary rise. In dry conditions, capillary action can lead to water moving upwards from the water table to the surface of the soil. This can create weak saturated zones on the slope surface, weakening the soil and increasing the risk of failure. Seepage. Seepage of water through the slope or along a fault line can cause erosion or reduce the soil's cohesion, weakening the slope stability. 6.2.3 Slope geometry. The geometry of the slope, including its height, angle, and shape, plays a critical role in its stability. Steeper slopes tend to be more susceptible to failure, especially when combined with adverse soil and hydrological conditions. Key slope geometry factors. Slope angle. The angle of the slope is one of the most significant factors affecting stability. As the slope angle increases, the driving forces, gravity, that tend to push the soil mass down the slope also increase. Typically, slopes steeper than the angle of internal friction, phi, of the soil are prone to failure. Slope height. Taller slopes are more prone to failure because they have a larger volume of material and increased driving forces. Deep slopes are also more likely to experience large deformations due to gravitational forces. Shape of the slope. The shape of the slope, whether concave, convex, or planar, affects how stresses and forces are distributed across the soil mass. Concave. Slopes may increase the concentration of stresses near the base of the slope, while convex slopes may help distribute stresses more evenly. Slope aspect. The orientation of the slope relative to environmental factors, such as the direction of rainfall or prevailing winds can influence its stability. 4. Example: south-facing slopes in the northern hemisphere may experience more solar radiation and evaporation, leading to drier conditions that can reduce stability, whereas north-facing slopes may retain moisture for longer periods, making them more prone to failure during wet conditions. 6.2.4 Geological and structural factors. The underlying geological structure and the presence of various features within the slope influence its stability. Faults, fractures, bedding planes, and soil layering can either enhance or undermine slope integrity. Key geological factors: bedding planes and stratigraphy, the arrangement and orientation of bedding. Planes can significantly impact slope stability. Slopes composed of layers of rock or soil with weak or low shear strength parallel to the slope face are particularly vulnerable to sliding along these planes. Rock types and fractures. Diorite rock types, e.g., shale, sandstone, limestone, have varying shear strengths, and the presence of fractures or faults within rocks can create planes of weakness. These features may facilitate sliding or cause localized failures within the slope. Tectonic activity. In tectonically active areas, the formation of new faults or the reactivation of existing faults can influence slope stability. The movement of fault lines can generate compressive or tensile stresses that either destabilize or cause slope failure. Fissures and cracks. The presence of fissures or cracks in the slope material, whether caused by weathering or other factors, can increase permeability and weaken the structural integrity of the slope, making it more susceptible to sliding. 6.2.5 External loads and human activity. Human activities, such as construction, excavation, or deforestation, can significantly alter the stability of slopes. Additionally, external loads, such as buildings or roads, can increase the driving forces on a slope, increasing the potential for failure. Key human and external factors. Construction and excavation. Excavating or constructing near the top or toe of a slope can alter the stress distribution within the slope and weaken its stability. Removal of material from the toe or adding loads at the top can change the balance of forces, leading to failure. Deforestation and vegetation loss. The removal of vegetation can have a detrimental effect on slope stability. Vegetation helps to bind the soil with root systems, reducing erosion and increasing shear strength. In areas where deforestation or land clearance occurs, slopes may become more prone to erosion, which can lead to failures. Vibrations and dynamic loads. External vibrations caused by TRA-IC construction activities or seismic events can destabilize slopes, particularly in loose or unconsolidated soils. The dynamic loading effect of these forces can induce Additional stresses that lead to failure. Artificial surcharge loads. Loading of the slope, whether due to infrastructure development, e.g., buildings, roads, or deposition of materials, can increase the shear forces acting on the slope, potentially leading to failure. 6.2.6 Environmental and climatic factors. Environmental and climatic factors, such as rainfall, temperature, and seasonal changes, can have significant effects on slope stability. Changes in moisture content, temperature fluctuations, and seasonal loading can lead to both long-term and short-term stability issues. Key environmental factors. Rainfall and seasonal changes. Intense rainfall events or seasonal changes in precipitation can increase the pore water pressure within a slope, reducing shear strength and making the slope more vulnerable to failure. Prolonged wet conditions can also cause soil saturation, reducing the soil's effective strength. Freeze and thaw cycles. In colder regions, freeze-thaw cycles can lead to the expansion and contraction of soil particles, causing them to weaken and become more prone to erosion and failure. Temperature fluctuations. Extreme temperature changes can cause soil swelling or shrinkage, especially in expansive clays, leading to instability in slopes. The differential movement of soils with varying moisture content can further exacerbate the risk of failure. 6.2.7 Conclusion. Slope stability is influenced by a combination of soil properties, water conditions, slope, geometry, geological factors, human activities, and environmental factors. A comprehensive understanding of these variables is essential for accurately assessing the stability of a slope and implementing appropriate mitigation measures. By considering all of these factors, engineers can design safe slopes and embankments, as well as develop effective strategies for managing landslide risks in vulnerable areas. Chapter 6. Slope Stability and Landslides. 6.3 Advanced Techniques in Landslide Prediction. Predicting landslides and slope failures is a complex process that requires the integration of various advanced techniques to understand and forecast slope behavior under a range of conditions. Traditional methods of predicting landslides rely on simple analysis of slope, geometry, soil properties, and water conditions, but more advanced approaches incorporate sophisticated numerical models, geophysical surveys, real-time monitoring, and machine learning techniques. In this section, we explore some of the most advanced methods currently used for landslide prediction. 6.3.1 Remote Sensing and GIS for Landslide Prediction. Remote Sensing and Geographic Information Systems, GIS, have revolutionized landslide prediction by enabling the collection of large-scale data and the ability to analyze terrain features, land use, and environmental changes over time. Key techniques. Satellite imagery. High-resolution satellite imagery can be used to map slopes, detect changes in vegetation, soil moisture, and surface displacement, and identify potential landslide-prone areas. Satellite-based radar, e.g., synthetic aperture radar or SAR, can detect ground movements over large areas and is particularly useful for monitoring landslides in remote regions. LiDAR, light detection and ranging LiDAR technology provides detailed, high-resolution topographic data of slopes, which can be used to create 3D models of the terrain. By comparing changes in the topography over time, LiDAR can detect subtle surface movements that may indicate slope instability. Aerial photography and drones. Drones equipped with high-resolution cameras or LiDAR sensors can capture detailed imagery of slopes, even in inaccessible areas. These technologies allow for precise monitoring and analysis of surface deformations and changes in slope geometry. GIS-based landslide hazard mapping. GIS enables the integration of multiple layers of data, such as slope steepness, geology, land use, rainfall, and historical landslide occurrences. By analyzing these layers, GIS can help identify areas at high risk for landslides and predict their likelihood of occurrence. Applications. Large-scale landslide hazard mapping in regions prone to landslides. Monitoring of surface deformation and terrain changes in real time. 6.3.2 Geophysical methods for subsurface investigation. Geophysical methods are valuable for investigating subsurface conditions without the need for intrusive drilling or excavation. These techniques help in understanding the distribution of soil types, groundwater conditions, and geological features that may influence slope stability. Key techniques. Seismic refraction and reflection. Seismic surveys are used to assess subsurface conditions by measuring the travel time of seismic waves through the ground. The variations in wave velocity can help identify soil layering, bedrock depth, and areas of weakness, such as faults or fractures, that may predispose slopes to failure. Ground-penetrating radar, GPR. GPR is a non-invasive technique that uses electromagnetic waves to image the subsurface. GPR can be used to detect changes in soil properties, identify fractures, and locate voids or weak zones within a slope that could lead to instability. Electrical resistivity imaging, ERI involves measuring the electrical resistivity of the soil to identify variations in moisture content, soil composition, and the presence of water or weak layers that could ECT slope stability. It is particularly useful for detecting areas of saturation and potential groundwater movement. Microgravity surveys. Microgravity surveys detect changes in the Earth's gravitational field caused by variations in subsurface densities. These changes can help identify voids, fractures, and weak zones within a slope, which may indicate potential landslide areas. Applications: mapping subsurface conditions in landslide-prone areas to detect weaknesses, identifying groundwater flow paths and changes in soil composition. 6.3.3 Numerical modeling for landslide prediction. Numerical modeling has become one of the most advanced tools for predicting slope failure. By simulating the physical processes that lead to landslides, engineers can better understand the complex interactions between soil properties, water conditions, and external forces. Key techniques: finite element method. THEM is widely used to model the behavior of slopes under various conditions. This method divides the slope into small elements and solves the equations of equilibrium for each element to predict stress, strain, and deformation. THEM can account for nonlinear soil behavior, pore water pressure, and the EX of errant loading conditions, making it ideal for complex slope stability. Analysis: finite d'Arrent's method, FDM divides the slope into a grid of points and calculates the movement of each point over time. This method can model large deformations and nonlinear behaviors and is particularly useful for analyzing dynamic conditions, such as earthquakes or rapid rainfall infiltration. Limit equilibrium method, LEM, with numerical integration. While LEM is a traditional method, it can be enhanced with numerical integration techniques such as the use of software that calculates the factor of safety of slopes by accounting for various failure surfaces and loadings. Discrete element method, DMDM, is used to simulate the behavior of individual particles within a slope. This method is particularly useful for analyzing granular soils and materials that exhibit non-continuum behavior, such as debris, flows, and rockfalls. DM can predict failure mechanisms at a particle level, providing insight into the progressive failure of slopes. Pore pressure and fluid flow modeling, simulating the movement of water through soil layers is a critical component of landslide prediction. Numerical models that include pore water pressure, groundwater flow, and drainage conditions can predict how changes in water content, ECT slope stability. Applications: simulating the response of slopes under various loading conditions, e.g., rain, seismic activity. Assessing the impact of changes in water flow, soil strength, and external forces on slope stability. 6.3.4 Real-time monitoring and early warning systems. Real-time monitoring and early warning systems are becoming increasingly important for predicting and mitigating the impact of landslides, particularly in high-risk areas. These systems collect continuous data from a network of sensors installed on or around the slope and use advanced algorithms to analyze the data and provide early warnings. Key techniques: slope monitoring systems. Sensors such as inclinometers, piezometers, and extensometers are installed in slopes to measure soil movement, pore water, pressure, and deformation. Inclinometers measure changes in slope angle, while piezometers monitor water pressure within the soil. Extensometers measure displacement across a slope, helping to detect early signs of failure. Geotechnical data logging and alarm systems. Real-time data collection. Systems continuously monitor changes in slope conditions, such as displacement or pore pressure, and send alerts to engineers or operators if a threshold is exceeded. These systems can trigger alarms, allowing for timely intervention and evacuation in the event of an imminent landslide. Ground-based radar. Ground-based radar systems, e.g., interferometric synthetic aperture radar or NSAR, are used to detect ground displacement over time. These systems are particularly useful in monitoring slow-moving landslides, providing detailed information on the rate and direction of slope movement. Satellite-based monitoring. NSAR technology uses satellite radar data to detect ground movement, enabling the monitoring of large-scale landslides or slow deformations over extensive areas. NSAR can provide valuable insights into the evolution of a landslide, even in remote or inaccessible regions. Applications. Monitoring slopes in real time to detect early signs of instability. Providing early warning signals to mitigate the impact of landslides on communities. And infrastructure. 6.3.5 Machine Learning and Artificial Intelligence in Landslide Prediction. Machine learning, ML, and artificial intelligence, AI, techniques are increasingly being used to predict landslides by analyzing large datasets and identifying patterns that may not be apparent through traditional methods. These technologies can improve the accuracy of landslide forecasting and provide real-time predictive capabilities. Key techniques. Predictive modeling using machine learning algorithms such as decision trees, random forests, and support vector machines can analyze large datasets containing information about past landslides, topography, soil properties, and environmental factors. By learning from historical data, these models can identify areas at high risk for future landslides and predict the likelihood of failure under direct conditions. Artificial neural networks. ANNs are a type of machine learning model that can be trained to recognize complex relationships between input variables, e.g., slope geometry, soil properties, rainfall, and the occurrence of landslides. ANNs are particularly useful for nonlinear problems and can provide real-time predictions based on new data inputs. Big data analytics. The integration of big data from multiple sources, such as remote sensing, geophysical surveys, and real-time monitoring systems, allows for more accurate landslide prediction. AI algorithms can analyze this vast amount of data in real time to make predictions based on patterns observed across multiple datasets. Applications: enhancing landslide risk assessment by analyzing large and complex datasets. Real-time prediction of landslide occurrence and magnitude, aiding in early warning systems. 6.3.6 Conclusion: advanced techniques in landslide prediction, such as remote sensing, geophysical methods, numerical modeling, real-time monitoring, and machine learning, are transforming the way geotechnical engineers assess and manage landslide risks. By integrating these innovative approaches, engineers can improve the accuracy of landslide forecasts, enhance early warning systems, and implement more effective mitigation strategies. As technology continues to advance, these techniques will play a crucial role in safeguarding communities and infrastructure from the devastating impacts of landslides. Chapter 6: Slope Stability and Landslides. 6.4 Slope Reinforcement and Stabilization Methods. Slope reinforcement and stabilization methods are critical techniques used in geotechnical engineering to enhance the stability of slopes and prevent landslides. These methods are designed to improve the strength and behavior of the soil, reduce the driving forces that lead to failure, and enhance the overall safety of the slope. In this section, we explore various advanced techniques used to stabilize and reinforce slopes, along with their applications and effectiveness. 6.4.1 Soil Nailing. Soil nailing is a widely used technique for stabilizing existing slopes, embankments, and cuttings, particularly in situations where landslides are a concern. It involves the insertion of steel reinforcement bars, nails, into the soil to improve its strength and cohesion. Process: nail installation. Steel rods, usually pre-tensioned, are drilled into the slope at a specific angle and length. The nails are typically installed from the surface or through drilling rigs. Grouting. Once the nails are inserted, grout is injected into the drilled holes to anchor the nails firmly within the soil mass. The grout serves to bond the nails with the surrounding soil, improving soil strength. Reinforced facing. Often, a reinforced facing, such as a mesh or shotcrete, is applied to the surface to provide additional stability and prevent erosion. Advantages: effective for stabilizing steep slopes with limited access. Minimal disturbance to the existing terrain and vegetation. Cost-effective for moderate to severe slopes. Applications: stabilizing embankments, cut slopes, and hillsides prone to erosion or landslides. Used in tunneling projects and excavation works to prevent slope failure. 6.4.2 Geogrids and geotextiles. Geogrids and geotextiles are synthetic materials used to reinforce slopes and improve their Stability. These materials are often used to create a layered system that distributes the weight of the slope and improves its shear strength. Key types. Geogrids. These are plastic or polyester grids used to reinforce soil. They work by providing lateral support and distributing stresses within the soil, preventing slope failure. Geotextiles. Geotextiles are fabric-like materials that help stabilize the soil by improving drainage and providing filtration. They also improve soil cohesion by preventing erosion. Applications. Geogrids are used to stabilize steep slopes and embankments, particularly in areas where heavy ice or construction is present. Geotextiles are used in landfills, erosion control systems, and roadsides to reduce soil erosion and improve water drainage. Advantages. Lightweight and easy to install. Improve soil structure and provide long-term stabilization. Effective for preventing erosion and improving drainage. 6.4.3 Retaining walls. Retaining walls are structures used to support the soil behind them, preventing it from sliding or collapsing. These walls can be made from a variety of materials, including concrete, stone, steel, and timber, and are designed to resist the lateral forces exerted by the slope. Types of retaining walls. Gravity walls. These are large, heavy walls made of stone, concrete, or masonry that rely on their weight to resist soil pressure. Cantilevered walls. These walls use a vertical stem and a base slab to resist lateral forces and prevent sliding. Sheet pile walls. Made from steel or concrete sheets, these walls are used in situations with limited space or high water levels, where gravity walls may not be practical. Reinforced soil walls. These walls combine soil reinforcement materials, such as geogrids, with a facing to create a stable structure. Applications. Stabilizing slopes along highways, railways, and other transportation infrastructure. Supporting embankments and cut slopes in urban areas. Advantages. Highly effective in preventing soil movement and maintaining slope stability. Provide structural support in urban and infrastructure projects. Can be aesthetically integrated into landscaping designs. 6.4.4 Soil grouting and injection techniques. Soil grouting involves the injection of a cementitious or chemical grout into the soil to increase its strength and improve its resistance to shear forces. This method is used to stabilize weak soils, prevent erosion, and reduce groundwater flow, which can compromise slope stability. Types of grouting. Cement grouting. Cement-based grouts are injected into the soil to increase its density and shear strength. This is commonly used in areas where the soil is loose or granular and needs additional support. Chemical grouting. Chemical grouts, such as sodium silicate or polyurethane, are used in situations where water flow needs to be stopped or where the soil needs to be solidified without altering its texture significantly. Compaction grouting. A thick grout mixture is injected into the soil to compact loose materials and increase density. This technique is particularly useful in areas with soft soils or loose sands. Applications: stabilizing deep foundations and improving soil properties in landslide-prone regions. Reducing the permeability of soils to control water flow and prevent erosion. Enhancing the shear strength of soils in areas of unstable slopes. Advantages: can stabilize soils with minimal excavation or disruption to the surface. Effective in addressing water-related slope issues. Provides long-term stabilization by solidifying soil or improving cohesion. 6.4.5 Rock bolting. Rock bolting is a technique commonly used in mountainous or rocky terrain to stabilize slopes and prevent rockfalls. It involves installing steel bolts or anchors into rock formations to increase the strength of the rock and hold it together. Process: bolt installation. Steel bolts or anchors are drilled into the rock mass and tension to create a strong bond between the rock layers. Grouting. The bolts are typically grouted to improve adhesion and prevent corrosion. Mesh or shotcrete. A reinforcing mesh or shotcrete is often applied over the surface to protect the slope from weathering and erosion. Advantages: effective for stabilizing steep, rocky slopes prone to rockfalls or sliding. Provides a long-lasting solution with minimal impact on the environment. Can be combined with other methods like shotcrete or geogrids for added stability. Applications: stabilizing rocky hillsides, CLIS, and mountain roads. Used in mining operations and tunnels to prevent rockfall and ensure worker safety. 6.4.6 Drainage control and surface water management. Managing surface water and groundwater flow is essential to slope stabilization, as excessive water can lead to soil erosion, increased pore pressure, and weaken soil shear strength. Drainage control systems help redirect water away from the slope, reducing the risk of failure. Techniques: French drains. A trench filled with gravel or perforated pipe used to channel water away from the slope. Subsurface drainage systems. These systems, such as horizontal drains or interceptor drains, remove water from the soil before it can accumulate and reduce stability. Surface drainage channels. Shallow channels or ditches placed on the surface to direct water runoff away from the slope face. Applications: used in combination with other stabilization methods to reduce the risk of water induced landslides. Effective in areas with high rainfall or where surface water accumulation is a concern. Advantages: reduces water-related instability by preventing the buildup of excess pore pressure. Can be implemented alongside other stabilization techniques. Helps improve soil cohesion and minimize erosion. 6.4.7 Vegetation and Bioengineering Techniques. Vegetation plays a crucial role in slope stabilization by providing root reinforcement, reducing surface erosion, and enhancing soil cohesion. Bioengineering combines plant-based methods with traditional engineering techniques to stabilize slopes naturally. Techniques: grass and ground cover. Planting grasses and other vegetation can help prevent soil erosion and reduce the impact of surface water runoff. Reinforced vegetative mats. Pre-grown mats of vegetation or synthetic mesh are used to stabilize slopes while promoting plant growth. Tree planting. Deep-rooted trees can provide additional soil stabilization and prevent shallow landslides. Advantages: environmentally friendly and sustainable approach to slope stabilization. Helps prevent erosion and improves the aesthetic value of the slope. Can be used in combination with other stabilization techniques for long-term stability. Applications: used on slopes in agricultural areas, highways, and landfills to prevent erosion. Effective for restoring vegetation in landslide-prone regions after stabilization. 6.4.8 Conclusion: slope reinforcement and stabilization methods are essential for preventing landslides and ensuring the long-term stability of slopes in geotechnical engineering. Techniques such as soil nailing, geogrid reinforcement, retaining walls, grouting, rock bolting, and drainage control provide a wide range of solutions to stabilize slopes under direct conditions. By selecting the appropriate method based on the site-specific conditions, engineers can effectively reduce the risk of slope failure, protect infrastructure, and enhance safety in landslide-prone areas. Chapter 6: Slope Stability and Landslides. 6.5 Case Studies in Slope Failures. Understanding past slope failures and landslides is crucial for improving the prediction and prevention of future incidents. Case studies provide valuable insights into the causes, impacts, and lessons learned from slope failures. In this section, we examine several notable case studies of slope failures around the world, focusing on the factors that contributed to the failures, the methods of mitigation employed, and the lessons that can be applied to future geotechnical engineering projects. 6.5.1 The Aberfan Disaster, 1966, South Wales, UK. Event Overview: the Aberfan disaster occurred on October 21, 1966, when a massive slurry heap made up of coal waste collapsed onto the village of Aberfan in South Wales. The failure of the slurry heap led to the burial of a school, a number of homes, and several other buildings, resulting in the deaths of 144 people, including 116 children. Contributing factors: heavy rainfall. Intense rainfall in the days preceding the failure saturated the waste heap, increasing its weight and causing it to become unstable. Improper heap construction. The slurry heap had been poorly constructed and was positioned on a slope above the village, with little consideration for its stability. Lack of drainage. There was insufficient drainage to control water infiltration, which increased the likelihood of failure. Mitigation measures. Slope remediation. After the disaster, authorities removed the remaining slurry heaps from the area and undertook slope stabilization measures to prevent future incidents. Stricter regulations. The Aberfan disaster led to changes in mining waste management practices in the UK, with stricter regulations governing the construction and monitoring of slurry heaps. Lessons learned. Proper management and monitoring of waste piles and slurry heaps are essential to prevent failures. Adequate drainage systems are critical in preventing saturation and instability in waste materials. Careful consideration of site selection and long-term stability of stockpiles or waste heaps is essential. 6.5.2 The Thistle Creek Landslide, 1997, Canada. Event overview. In 1997, a significant landslide occurred along Thistle Creek in British Columbia, Canada. The failure caused extensive damage to infrastructure, including roads and power lines. The landslide affected a region that had been previously identified as having a history of slope instability. Contributing factors: heavy rainfall. The area experienced heavy rainfall in the days leading up to the failure, which saturated the soil and triggered the landslide. Natural terrain features. The natural topography, including steep slopes and loose soil, predisposed the area to landslide risks. Undetected groundwater movement. Groundwater movement beneath the slope, along with water from the rainfall, created excess pore pressure, reducing the soil's shear strength and contributing to the landslide. Mitigation measures. Slope stabilization. After the landslide, geotechnical engineers employed a range of techniques, including soil nailing, drainage improvements, and the installation of retaining structures to stabilize the slope. Monitoring systems. Continuous monitoring systems were installed to detect any further movement or signs of instability in the area, allowing for early warning and mitigation if necessary. Lessons learned. Detailed site investigation and ongoing monitoring are crucial in areas prone to slope failure, especially those with complex groundwater conditions. Heavy rainfall and groundwater movement should be considered as key factors in the design and analysis of slope stability. Early warning systems can help mitigate risks to infrastructure and public safety. 6.5.3 The Veja Dam Disaster, 1963, Italy. Event overview. The Vajont Dam disaster occurred on October 9, 1963, in northern Italy, when a massive landslide, triggered by heavy rainfall and geological conditions, slid into the reservoir behind the Vajont Dam. The slide displaced a vast amount of water, which overflowed the dam's crest, resulting in the inundation of the valley below and the loss of over 2,000 lives. Contributing factors: geological instability. The area surrounding the dam had underlying geological weaknesses, including a fault zone and loose rock layers, which made the slope highly susceptible to failure. Heavy rainfall and reservoir-induced seismicity. Rainfall had saturated the rock formations, and the rising water levels in the dam reservoir exerted additional pressure on the already unstable slopes. Inadequate risk assessment. While the dam itself was considered structurally sound, insufficient attention was paid to the surrounding slope stability, leading to a critical oversight in the risk assessment process. Mitigation measures. Post-disaster reassessments. After the disaster, the event prompted a reassessment of dam and slope safety in similar contexts, including the need for more comprehensive risk assessments that consider all contributing factors, including geological instability and hydrological conditions. Revised design guidelines. The disaster led to the development of new design guidelines for dam construction and the surrounding areas, placing more emphasis on slope stability and detailed geological investigations. Lessons learned. A holistic approach to risk assessment that includes geological, hydrological, and structural factors is essential for large infrastructure projects, particularly dams. Monitoring and controlling water levels in reservoirs can have a significant impact on slope stability, and therefore, water-induced forces should be closely managed. Comprehensive monitoring systems for both the structure and surrounding slopes are necessary to identify risks early and mitigate potential disasters. 6.5 Point for the 1995 Sidoarjo mudflow, Indonesia. Event overview. The Sidoarjo mudflow, also known as the Lapindo mudflow, began in May 2006 in East Java, Indonesia. The event was triggered by drilling activities at a gas exploration site and resulted in the eruption of hot mud, which engulfed villages, farms, and roads. The mudflow continued for several years, leading to widespread displacement and damage. Contributing factors. Drilling activities. The drilling for natural gas led to the unexpected release of pressurized mud and gas from underground, which caused the eruption of mud onto the surface. Geological conditions. The region's geological conditions, including the presence of natural faults and a weak subsurface layer, contributed to the instability of the area and the rapid spread of the mudflow. Lack of proper safety protocols. The drilling operation lacked sufficient safety protocols, and risk assessments related to the possibility of a mudflow. Mitigation measures. Containment and diversion. Earts were made to divert the mudflow away from populated areas through the construction of embankments and barriers. Monitoring and control. After the event, an extensive monitoring system was put in place to study the behavior of the mudflow and prevent further damage. Lessons learned. The importance of proper risk assessment and safety measures in industrial operations such as drilling and mining. A clear understanding of the local geology is critical to anticipate and mitigate risks associated with drilling or excavation activities. Immediate response and monitoring systems are essential to control and limit the spread of such events. 6.5.5 The 2014 Oso landslide, Washington, USA. Event overview. The Oso landslide, which occurred on March 22, 2014, in Washington State, was one of the deadliest landslides in U.S. history. The landslide, which struck the small community of Oso, was triggered by heavy rainfall and underlying geologic conditions. The slide resulted in the deaths of 43 people and extensive damage to infrastructure. Contributing factors: heavy rainfall. Prolonged rainfall prior to the slide caused the soil to become saturated and weakened the underlying soils, making them prone to sliding. Geological conditions. The slope consisted of unstable glacial deposits and poorly consolidated sediments, which were prone to failure under conditions of heavy rainfall. Lack of early warning systems. While landslides were a known risk in the area, there were no SUISH early warning systems in place to alert residents to the imminent danger. Mitigation measures. Slope monitoring. After the event, a series of slope monitoring systems were established to provide real-time data on soil conditions and early warning of potential landslides. Improved risk mapping, geotechnical assessments, and updated hazard mapping were used to better identify high-risk areas and guide future development and mitigation efforts. Lessons learned. The importance of early warning systems and communication to residents in landslide-prone areas. Comprehensive geotechnical studies and monitoring are critical to identifying and mitigating risks in areas with unstable slopes. Community education and planning for landslide risks can save lives and reduce damage in the event of a disaster. 6.5.6 Conclusion. Case studies of slope failures offer invaluable insights into the complexities of slope stability, highlighting the numerous factors that can lead to catastrophic events. By analyzing these case studies, engineers and planners can develop better methods for preventing, mitigating, and responding to landslides. Key lessons from these events. Emphasize the importance of thorough site investigations, effective risk assessment, early warning systems, and the need for ongoing monitoring and maintenance to ensure the safety of slopes and surrounding infrastructure. Chapter 7: Geotechnical Earthquake Engineering. 7.1 Soil Structure Interaction in Seismic Conditions. Soil structure interaction, SSI, is a critical aspect of geotechnical earthquake engineering, especially in seismic regions. It refers to the interaction between the soil and the structures built on it during seismic events. When an earthquake occurs, the ground motion acts both the soil and the structures, and vice versa, influencing the overall response of the system. Understanding soil structure interaction is essential for designing and constructing buildings, bridges, and other infrastructure that can withstand the forces generated by earthquakes. In this section, we explore the fundamentals of soil structure interaction in seismic conditions, including the key concepts, factors affecting SSI, and methods used to analyze and mitigate the impact of earthquakes on structures. 7.1.1 Key Concepts in Soil Structure Interaction. Soil structure interaction involves the dynamic interaction between the foundation of a structure and the underlying soil during an earthquake. The interaction can result in changes in the structure's response to seismic forces, such as amplified vibrations, settlement, or tilting, depending on the soil's properties and the type of structure. Key concepts: foundation soil interaction. The foundation of a structure, whether shallow or deep, transmits seismic forces to the underlying soil. The soil's response can alter the load distribution and the performance of the structure. Wave propagation. Seismic waves generated by the earthquake propagate through the ground and the soil, causing shear strains and displacements. The interaction between these waves and the foundation can modify the response of the structure. Inertial interaction. The inertia of the structure, its resistance to motion, influences the interaction with the soil during seismic events. A heavier structure may impose greater forces on the foundation, while a lighter structure may exhibit different dynamic responses. Dynamic amplification. In some cases, the soil's dynamic properties may amplify seismic waves, causing larger ground motions at the foundation level than those recorded at the ground surface. 7.1.2 Factors affecting soil structure interaction in seismic conditions. Several factors influence the nature and intensity of soil structure interaction during an earthquake, including the properties of the soil, the type of foundation, and the characteristics of the structure. 1. Soil properties. Shear modulus and damping. The steepness, shear modulus, and damping characteristics of the soil play a critical role in determining how the soil will deform under seismic loads. Strong, steep soils transmit seismic waves more efficiently, while soft, loose soils may amplify ground motion and lead to greater displacement. Soil type: cohesionless soils, such as sands, and cohesive soils, such as clays, exhibit different dynamic behaviors. Sand, for example, may experience liquefaction under certain conditions, while clay may exhibit larger deformations. Soil structure interface: the nature of the contact between the soil and the foundation, whether the interface is smooth or rough, influences the frictional resistance and the relative motion between the two elements. 2. Foundation type: shallow foundations. These include mat foundations, spread footings, and slab foundations, which are typically more sensitive to the EX of SSI. Shallow foundations may undergo significant settlements or tilting during an earthquake if the underlying soil is not adequately designed to resist seismic forces. Deep foundations: pile foundations, drilled shafts, and caissons are designed to transfer loads deeper into the soil and may perform better in seismic conditions, particularly in soft or liquefiable soils. Foundation flexibility: a flexible foundation allows more relative motion between the soil and the structure, leading to a more significant EECT on seismic response. In contrast, a rigid foundation may reduce the impact of soil structure interaction by restricting the relative motion. 3. Structural characteristics: building type: the type and design of the structure, e.g., high-rise buildings, bridges, or low-rise residential buildings, EECT its interaction with the foundation and the soil. Taller buildings may experience greater sway during an earthquake, while shorter buildings may be more rigid. Foundation stiffness: a steer foundation will provide more resistance to seismic forces, while a flexible foundation may result in greater movement during an earthquake. Seismic mass and damping: the total mass of the structure and its ability to dissipate seismic energy through damping mechanisms are crucial factors in determining the extent of seismic shaking experienced by the building. 4. Site and ground conditions: site location: the geographical location of the site, proximity to fault lines, and local seismic activity influence the intensity of ground shaking and the severity of the interaction. Liquefaction potential: in regions with loose, saturated sandy soils, the potential for liquefaction can significantly alter the response of the soil structure system. Liquefaction can cause settlement, tilting, and even the failure of foundations. 7.1.3 Methods of analyzing soil structure interaction. Several analytical methods are used to assess and predict the EX of soil structure interaction in seismic conditions. These methods range from simplified analytical approaches to complex numerical simulations, depending on the complexity of the system and the required level of accuracy. 1. Simplified analytical methods. Spring mass models. These models treat the soil as a series of springs and the structure as a mass, allowing for a simplified analysis of the interaction. The soil's steepness is represented by the spring constant, and the damping is incorporated into the system as damping coefficients. Winkler model. The Winkler model is a simplified method in which the soil is assumed to behave like a series of independent springs. While this approach is useful for preliminary assessments, it may not capture all the complexities of the interaction, particularly for complex or large systems. 2. Dynamic analysis. Time history analysis. Time history analysis involves applying ground motion data, accelerograms, to a structural system and analyzing its response over time. This approach is more accurate and provides detailed insights into the behavior of the system during an earthquake. Response spectrum analysis. This method calculates the maximum response of a structure to earthquake loading by considering the dynamic characteristics of the soil and structure. It is typically used in conjunction with other methods to predict peak displacements, accelerations, and forces. 3. Finite element modeling (FEM). Finite element analysis (FEM) is a more advanced numerical method used to model complex soil structure interaction problems. It divides the entire system into smaller, manageable elements and solves the equations of motion for each element. This method allows for a more detailed and accurate analysis of the response, including soil nonlinearity, foundation flexibility, and structural deformations. Nonlinear soil behavior. FEM can also account for nonlinear soil behavior under seismic loads, such as soil plasticity, yielding, and liquefaction, providing a more realistic representation of soil structure interaction during earthquakes. 4. Dynamic soil structure interaction models. Coupled analysis. In coupled soil structure interaction analysis, the soil and structure are modeled as a single, integrated system. This approach considers the dynamic behavior of both the soil and structure simultaneously, providing a more accurate representation of the overall system's response during an earthquake. Boundary element methods. BM in some cases, boundary element methods are used to model large-scale soil structure interaction problems, particularly for very large structures, as they reduce the computational load compared to traditional finite element analysis. 7.1.4 Mitigation strategies for soil structure interaction. To mitigate the impact of soil structure interaction on structures during earthquakes, several techniques and strategies can be employed. 1. Foundation design. Deep foundations, pile foundations, drilled shafts, and caissons can provide better seismic performance, especially in areas with weak or liquefiable soils. Base isolation. Base isolation techniques involve placing flexible bearings or isolators between the foundation and the superstructure. This allows the building to move independently of the ground motion, reducing seismic forces and protecting the structure from shaking. Mat foundations. Large mat foundations distribute seismic loads more evenly across the soil and help reduce differential settlement, which can cause structural damage. 2. Soil improvement. Soil compaction. Compaction of loose soils can increase their strength and reduce settlement during seismic shaking. Grouting and stabilization. Techniques such as cement grouting or chemical stabilization can improve the strength and steadiness of soils, particularly in areas with weak or liquefiable soils. Vibrocompaction and vibrodisplacement. These techniques densify loose, granular soils, reducing the risk of liquefaction and enhancing their seismic stability. 3. Seismic damping systems. Damping devices. Tuned mass dampers, viscous dampers, or friction dampers can be installed in buildings to absorb seismic energy and reduce vibrations, improving the structure's seismic performance. Viscoelastic materials. The use of viscoelastic materials in the foundation or structure can provide damping and reduce the impact of soil-structure interaction. 7.1.5 Conclusion. Soil-structure interaction in seismic conditions is a complex phenomenon that significantly influences the response of structures during an earthquake. A comprehensive understanding of the factors affecting SSI, including soil properties, foundation design, structural characteristics, and site conditions, is essential for designing earthquake-resistant structures. Advanced analytical methods, such as time history analysis, finite element modeling, and coupled analyses, provide valuable tools for assessing the impact of seismic forces on soil structure systems. By incorporating effective mitigation strategies, engineers can design safer and more resilient infrastructure that minimizes the risks associated with soil structure interaction during seismic events. Chapter 7. Geotechnical Earthquake Engineering. 7.2 Liquefaction Potential and Mitigation. Liquefaction is a phenomenon where saturated, loose, fine-grained soils lose their strength and behave like a liquid during an earthquake. This sudden loss of strength can lead to severe consequences such as foundation settlement, tilting, and even the collapse of structures. Liquefaction primarily occurs in saturated, sandy soils that are subject to intense shaking during an earthquake. Understanding the potential for liquefaction and employing mitigation strategies is critical for ensuring the safety of structures in earthquake-prone regions. In this section, we explore the causes and factors influencing liquefaction, methods for assessing liquefaction potential, and the various mitigation techniques used to prevent or reduce liquefaction-related damage. 7.2.1 Causes and mechanisms of liquefaction. Liquefaction occurs when the pore water pressure in saturated soils increases during seismic shaking, reducing the ejective stress between soil particles. As a result, the soil loses its ability to resist shear forces, and the soil mass behaves like a liquid. The primary causes of liquefaction include 1. Seismic shaking. During an earthquake, ground motion induces cyclic shear stresses in the soil. In saturated, loose, granular soils, this shaking can increase pore water pressure, which reduces the ejective stress and weakens the soil. 2. Saturation of soil. Liquefaction is most likely to occur in soils that are fully saturated or nearly saturated with water. The presence of water in the pore spaces allows pore pressure to build up more readily under seismic shaking. 3. Soil type and gradation. Liquefaction typically occurs in sandy soils with fine to medium grains, though siltous soils can also liquefy under certain conditions. Well, graded sands or coarse-grained soils with high void ratios are more susceptible to liquefaction. 4. Low ejective stress. For liquefaction to occur, the ejective stress between soil particles must be low. This often happens when the pore water pressure becomes significant enough to counteract the weight of the overlying soil, reducing the soil's shear strength. 7.2.2 Factors affecting liquefaction potential. Several factors influence the likelihood and severity of liquefaction during an earthquake, including soil properties, the intensity of ground shaking, and groundwater conditions. 1. Soil type and particle size distribution. Loose sands and silts are more prone to liquefaction than dense or cemented soils. Fine-grained soils with low permeability, such as silts and clays, are less likely to liquefy, but they may still exhibit strength loss under certain conditions, such as high pore pressure or high water content. 2. Soil density and void ratio. Loose, low-density soils are more susceptible to liquefaction than dense, compacted soils. A high void ratio, the ratio of air to soil particles, increases the likelihood of liquefaction as it allows more space for pore water buildup. 3. Groundwater table. Liquefaction typically occurs in soils that are near or below the water table, where pore spaces are fully saturated with water. The closer the groundwater table is to the surface, the higher the risk of liquefaction. 4. Magnitude and duration of earthquake. The severity of ground shaking, measured by the earthquake's magnitude and duration, directly influences liquefaction potential. Strong, prolonged shaking increases the likelihood of pore pressure buildup and failure of the soil structure. 5. Depth of soil layer. Liquefaction typically occurs in shallow soils, as deeper soils experience less shaking. However, liquefaction can still occur at greater depths if the soil is loosely packed and the shaking is intense enough. 7.2.3 Methods for assessing liquefaction potential. To evaluate the potential for liquefaction, geotechnical engineers use various methods and techniques that take into account soil properties, seismic conditions, and historical performance during earthquakes. Common methods include 1. Standard Penetration Test (SPT). The SPT is one of the most widely used methods for assessing liquefaction potential. It involves driving a sample tube, split spoon, into the soil using a hammer and measuring the number of blows required to achieve a certain penetration depth. The SPT blow count is then correlated with liquefaction susceptibility. Lower blow counts typically indicate a higher likelihood of liquefaction. 2. Cone Penetration Test (CPT). The CPT involves pushing a cone-shaped probe into the ground and measuring the resistance to penetration, the tip resistance and sleeve. Friction data obtained from the test are used to evaluate soil properties and the likelihood of liquefaction. The CPT is often preferred over SPT for its continuous measurement and more accurate profiling. 3. Field observations. Post-earthquake field observations, including the identification of surface ruptures, sand boils, and lateral spreading, can provide valuable insights into liquefaction behavior and help validate laboratory and field tests. 4. Pore pressure and shear wave velocity measurements. Measuring changes in pore water pressure during cyclic loading can help assess liquefaction potential. Shear wave velocity measurements obtained through methods such as seismic refraction or downhole testing can provide information on soil steepness and the likelihood of liquefaction. 5. Liquefaction Potential Index (LPI). The Liquefaction Potential Index (LPI) is a composite index used to quantify liquefaction susceptibility based on factors such as SPT blow counts, depth, and soil type. It is often used for rapid site assessments and hazard analysis. 7.2.4 Mitigation Techniques for Liquefaction. To reduce or prevent the effects of liquefaction on structures and infrastructure, several mitigation methods can be implemented. These techniques focus on either improving soil conditions to reduce liquefaction susceptibility or enhancing the design of foundations and structures to withstand liquefaction (EX). 1. Soil improvement and compaction. Densification. Increasing the density of loose soils can reduce liquefaction potential. Techniques such as vibrocompaction, dynamic compaction, and compaction grouting can be used to compact sandy soils, reducing their void ratio and improving their resistance to liquefaction. Grouting. Grouting techniques, such as cement or chemical grouting, can be used to improve the strength and steepness of the soil. Grout injection increases soil density and cohesion, which reduces the potential for liquefaction. Soil stabilization. Chemical additives, such as lime or cement, can be mixed with soil to improve its shear strength and resistance to liquefaction. 2. Deep foundations. Pile foundations. Piles can be used to transfer loads to deeper, more stable soil layers that are less susceptible to liquefaction. Piles are particularly effective in areas where the liquefaction-prone soil layer is shallow. Drilled shafts. Drilled shafts where caissons can be used to anchor structures to deep, stable strata, providing support even if the upper layers liquefy during an earthquake. 3. Ground improvement techniques. Vibro replacement. Vibro replacement techniques, such as stone columns or gravel piles, can be used to improve the strength of liquefiable soils. These methods increase the soil's shear strength by introducing dense materials into the soil profile. Compaction grouting. This method involves injecting a grout mixture into the soil under pressure to densify loose, saturated sands and silts, improving the soil's resistance to liquefaction. Jet grouting. Jet grouting involves injecting a high-pressure jet of grout into the soil to create solidified columns that increase soil strength and reduce liquefaction potential. 4. Surface treatment and reinforcement. Reinforced mat foundations. Mat foundations reinforced with geogrids or other reinforcement materials can distribute seismic forces more evenly across the surface and help prevent settlement or tilting due to liquefaction. Lateral spread control. In areas susceptible to lateral spreading due to liquefaction, techniques such as trenching, retaining walls, or deep soil mixing can be used to control horizontal displacements and prevent movement of the ground surface. 5. Base isolation. Seismic base isolation. Base isolation involves placing flexible bearings or isolators between the foundation and superstructure, allowing the structure to move independently of the ground motion. This can mitigate the effects of liquefaction by allowing the structure to avoid or reduce the forces generated by ground shaking. 7.2.5 Conclusion. Liquefaction is a significant concern in geotechnical earthquake engineering, particularly in areas with loose, saturated soils. It can cause severe structural damage, including foundation settlement, tilting, and the collapse of buildings. Assessing liquefaction potential is essential for the design and safety of structures in earthquake-prone regions. Various methods, such as SPT, CPT, and shear wave velocity measurements, are used to evaluate liquefaction susceptibility, while mitigation techniques such as soil improvement, deep foundations, and base isolation can reduce the risk and consequences of liquefaction. by understanding the causes, assessing the risks, and employing effective mitigation measures, engineers can design more resilient infrastructure and safeguard communities from the effects of liquefaction during seismic events. Chapter 7: Geotechnical Earthquake Engineering. 7.3 Seismic Site Response Analysis. Seismic site response analysis is a critical tool in geotechnical earthquake engineering, used to assess how local soil conditions amplify or attenuate seismic waves during an earthquake. The ground shaking experienced at a site is heavily influenced by the properties of the underlying soil and rock. Understanding how seismic waves interact with the soil layers can help predict the level of shaking and potential damage to structures, as well as guide mitigation measures for minimizing earthquake-related risks. In this section, we explore the principles of seismic site response analysis, methods used to model site response, and how these analyses are applied in the design of earthquake resistant structures. 7.3.1 Principles of Seismic Site Response. Seismic site response refers to the way in which seismic waves, P waves, S waves, and surface waves propagate through a site and the changes they undergo as they interact with the site's geological and soil properties. When an earthquake occurs, the seismic waves travel from the epicenter, but the local soil conditions can amplify or reduce the shaking, significantly affecting the seismic response at the surface. Key principles of site response. 1. Wave propagation. Seismic waves move through the earth at different speeds depending on the medium, soil, or rock through which they travel. As seismic waves move from deeper bedrock to shallower soil layers, their characteristics, such as amplitude and frequency content, may change. 2. Amplification of ground motion. Soft soils and sedimentary layers tend to amplify seismic waves, especially in the lower frequency range. The extent of amplification depends on the soil steepness, damping properties, and depth. The site's fundamental frequency, determined by soil steepness and layer thickness, can amplify certain frequency components of the seismic waves, which can resonate with the frequencies of buildings and infrastructure. 3. Frequency-dependent EX. The frequency content of the seismic waves is important when assessing site response. For example, soil layers may amplify lower frequencies more than higher frequencies, which can have a greater impact on structures designed with specific resonant frequencies. 4. Nonlinear soil behavior. Soil behavior during seismic shaking is often nonlinear, especially for soft, loose, or saturated soils. As the shaking intensity increases, soils may experience plastic deformation, which can reduce their steepness and modify the seismic response. This requires nonlinear models in the analysis to accurately predict soil behavior under dynamic loading. 7.3.2 Methods for seismic site response analysis. Various analytical techniques and computational models are used to perform seismic site response analysis. The selection of the method depends on factors such as the complexity of the site, the level of detail required, and the available data. 1. 1D site response analysis. 1D site response analysis is used to model the behavior of a single vertical column of soil. This approach is commonly applied when the soil profile is relatively simple and can be approximated as a series of horizontal layers. The analysis focuses on the propagation of seismic waves through the layers and evaluates the resulting ground motion at the surface. Key steps in 1D site response analysis. Input ground motion, the seismic motion at the bedrock or bottom of the soil. Profile is used as the input motion. Soil layers and properties. The soil profile, including the thickness, steepness, shear modulus, damping, and density of each layer is defined. The material properties of each layer are essential in determining the seismic wave propagation. Dynamic amplification. The wave propagation through each layer is simulated, accounting for changes in wave velocity and the nonlinear behavior of the soil. Amplification is calculated at the surface, where the results are compared with the input ground motion. Software tools for 1D analysis. Programs like Shake and DeepSoil are commonly used for 1D site response analysis. These tools allow engineers to model soil layers, define input ground motions, and simulate the resulting surface shaking. 2. 2D and 3D site response analysis. 2D and 3D site response analysis are more advanced methods used to evaluate the seismic response of a site with more complex geometries, including lateral variations in soil properties, layered profiles, or irregular surface features, such as slopes, valleys, or ridges. These methods provide a more detailed and accurate prediction of ground shaking, especially in cases where lateral heterogeneity is significant. Key considerations for 2D and 3D analysis. Lateral variability. These analyses consider the lateral variation in soil properties, e.g., steepness, density, and how the seismic waves are affected by changes in soil composition. Topographical EX. In mountainous or uneven terrain, the topography can influence the propagation of seismic waves. Surface waves can be amplified at the crest of a hill or reduced in valleys, creating complex ground motion patterns. Wave reflection and diffraction. The interaction of seismic waves with irregular boundaries or interfaces can lead to wave reflection, diffraction, and focusing. EX, which are better captured in 2D and 3D models. Software tools for 2D/3D analysis. Programs like FLSC, fast Lagrangian analysis of continua, and OpenCSAR, used for 2D and 3D dynamic analyses. These tools can simulate the effects of lateral variability and irregular geometries on seismic waves. 3. Nonlinear site response analysis. Nonlinear site response analysis is required to model soil behavior under strong shaking conditions, where soil steadiness and damping properties change significantly due to plastic deformation. In real-world earthquakes, the soils may experience large deformations, and a linear model would not accurately represent the behavior of the soil. Steps for nonlinear analysis. Nonlinear material models. Nonlinear models, such as the equivalent linear or fully nonlinear methods, are used to simulate changes in soil steadiness and damping during the seismic event. These models allow the soil shear modulus and damping ratio to vary depending on the level of strain induced by the earthquake. Dynamic soil properties. Soil properties, including the shear modulus degradation and hysteretic damping, are defined for each layer to capture nonlinear effects. Strain-dependent behavior. Nonlinear site response analysis takes into account the strain-dependent behavior of the soil, particularly in soft soils or those with significant pore pressure buildup. Software tools for nonlinear analysis. Tools like Shake 2000, which includes a nonlinear version, and FLSE are often used to perform nonlinear site response analysis. 7.3.3 Applications of seismic site response analysis. Seismic site response analysis is crucial for a variety of applications in geotechnical engineering and earthquake engineering. Some key applications include 1. Design of earthquake-resistant structures. Site response analysis helps determine the level of ground shaking a structure is likely to experience, enabling engineers to design buildings, bridges, and other infrastructure to withstand these forces. The analysis can identify areas with high amplification of seismic waves, guiding the design of appropriate foundations or seismic isolators. 2. Assessment of ground motion hazards. Site-specific ground motion prediction is essential for seismic hazard assessments. By simulating the site's response to various earthquake scenarios, engineers can predict the expected ground shaking at the surface, aiding in the development of seismic risk maps for urban planning and emergency preparedness. 3. Liquefaction hazard analysis. Seismic site response analysis helps to evaluate the potential for liquefaction in a site by modeling the intensity and duration of shaking. Strong ground motion from site response analysis can be used to assess whether liquefaction is likely to occur in specific soil layers, particularly in loose, saturated sands. 4. Retrofit and rehabilitation of existing structures. For existing structures, Site response analysis can be used to assess the need for retrofitting or strengthening to improve earthquake performance. If the site response indicates significant amplification of seismic waves, the structure may require upgrades, such as base isolation or foundation. Reinforcement. 5. Urban planning and zoning. Site response analysis is an important tool for urban planners and authorities when evaluating the suitability of a location for new construction. Areas with a high risk of amplification may be designated as less suitable for development or may require special seismic mitigation measures in construction codes. 7.3.4 Conclusion. Seismic site response analysis is an essential part of geotechnical earthquake engineering, providing valuable information on how local soil and rock conditions influence ground shaking during an earthquake. By understanding the behavior of seismic waves as they interact with the errant soil layers, engineers can predict the level of seismic shaking a site will experience, assess the potential for damage, and design resilient infrastructure to withstand earthquakes. Whether using 1D, 2D, or 3D models, the results of site response analysis play a crucial role in ensuring the safety and performance of structures in earthquake-prone regions. Chapter 7. Geotechnical Earthquake Engineering. 7.4 Ground Motion and Seismic Hazard Assessment. Ground motion and seismic hazard assessment are integral components of geotechnical earthquake engineering, providing essential information for the design and evaluation of structures in earthquake-prone regions. Ground motion refers to the movement of the ground during an earthquake, while seismic hazard assessment aims to quantify the likelihood of earthquake-related ground shaking and its potential impact on a specific site. This section delves into the methods and tools used for ground motion analysis and seismic hazard assessment, focusing on how these assessments help engineers design earthquake-resistant structures, prepare for earthquake events, and mitigate risks associated with seismic hazards. 7.4.1 Ground motion characteristics. Ground motion is the result of seismic waves propagating from the source of an earthquake, and it varies significantly depending on factors such as the earthquake's size, distance from the epicenter, soil conditions, and local topography. Understanding the characteristics of ground motion is essential for evaluating how buildings and infrastructure will respond to seismic events. Key characteristics of ground motion. 1. Amplitude. The amplitude of ground motion refers to the peak displacement, velocity, or acceleration of the ground. The maximum amplitude often correlates with the intensity of the shaking and is critical in assessing the potential for structural damage. 2. Frequency content. The frequency content of seismic waves varies depending on the earthquake source and propagation path. Low-frequency waves tend to travel long distances and can cause damage to tall buildings, while high-frequency waves are more likely to ECT shorter, steer structures. The resonance of structures with specific frequencies of ground motion is an important consideration in seismic design. 3. Duration. The duration of shaking refers to the length of time over which the ground motion persists. Longer shaking durations can result in more extensive damage, particularly in structures and soil that experience cumulative EX over time. 4. Wave types. P waves. Primary waves. These are the fastest seismic waves and are typically the first to arrive at a site. They cause compressional motion in the soil and are usually less damaging than other waves. S waves. Secondary waves. These waves cause shear motion and are slower than P waves. S waves are typically more destructive as they produce ground displacement in two perpendicular directions. Surface waves. These waves travel along the Earth's surface and often cause the most significant ground motion, especially in softer soils. They include love waves, horizontal shear waves, and Rayleigh waves, elliptical motion waves. 5. Peak ground acceleration, PGA. PGA is a key measure of ground shaking, quantifying the maximum acceleration experienced at the surface during an earthquake. PGA is directly correlated with the potential for structural damage and is a primary parameter used in earthquake-resistant design codes. 7.4.2 Methods for ground motion prediction. The prediction of ground motion at a site involves using statistical models that estimate the expected amplitude, frequency content, and duration of seismic waves. These predictions rely on seismic source models, the distance from the fault, and the site conditions. 1. Ground motion prediction equations, GMPs. GMPs are empirical relationships developed through the analysis of earthquake data that predict the ground shaking intensity at a specific site based on the earthquake magnitude, distance from the source, and site conditions. These equations are widely used to estimate peak ground acceleration, PGA, spectral acceleration, SA, and other ground motion parameters for a given location. Common GMPs include those developed by groups such as Campbell and Bozornia, Abrahamson and Silva, and Zhao et al., which are incorporated into seismic hazard models and design codes. 2. Site amplification factors. Site-specific amplification factors are used to adjust ground motion predictions for local soil conditions. Soft soils tend to amplify seismic waves, while hard rock sites generally experience less amplification. The site amplification factor can be determined using empirical correlations based on the shear wave velocity (Vs) of the soil profile, or by performing seismic site response analysis. 3. Fourier spectrum and response spectra. The Fourier spectrum provides a frequency-based representation of ground motion, while the response spectrum describes the peak response of a single degree of freedom oscillator subjected to the ground motion. Both methods are used to assess the dynamic response of structures to seismic shaking, with the response spectrum being particularly useful in design applications. 7.4.3 Seismic Hazard Assessment. Seismic hazard assessment is the process of quantifying the probability of earthquake ground shaking of varying intensities occurring at a specific location over a given time period. This assessment provides essential data for designing earthquake-resistant structures, zoning for risk, and developing emergency preparedness strategies. 1. Seismic hazard curves. Seismic hazard curves represent the probability of exceeding a specific level of ground shaking, e.g., PGA, over a given time period, usually 50 or 100 years. These curves are developed through the integration of earthquake source models, ground motion prediction equations, and site conditions. 2. Probabilistic Seismic Hazard Analysis (PSHA). PSHA is the most common method for evaluating seismic hazards. It combines the likelihood of different earthquake scenarios in terms of magnitude, distance, and fault characteristics with the expected ground motion at a site. The output of a PSHA is typically presented as hazard curves or maps, which depict the probability of exceeding specific levels of ground shaking over a given time frame. Steps in PSHA. Source characterization. Identify and characterize seismic sources, e.g., faults, that can produce earthquakes in the region. This involves defining the frequency and magnitude of earthquakes associated with each source. Ground motion prediction. Use GMPs to predict the expected ground motion at the site for each earthquake scenario. Integration. Combine the seismic source characteristics and ground motion predictions with probabilities of occurrence to assess the total seismic hazard at the site. 3. Deterministic Seismic Hazard Analysis (DSHA). DSHA evaluates the potential ground shaking at a site based on the assumption of a specific earthquake scenario, such as the worst-case earthquake from a nearby fault. While PSHA provides a probabilistic view of seismic hazard, DSHA focuses on a single event that is likely to cause significant shaking at the site. 4. Seismic hazard maps. Seismic hazard maps provide a geographic representation of seismic hazard across a region. These maps typically show the expected level of shaking, e.g., PGA, spectral acceleration, with a given probability of exceedance over a specified time period. Seismic hazard maps are often used for land use planning, building codes, and risk management. 5. Earthquake loss estimation. Ground motion and seismic hazard assessments are often linked to earthquake loss. Estimation, which estimates the potential damage to infrastructure, buildings, and populations. These estimates are crucial for emergency response planning, insurance modeling, and disaster risk reduction (EORTS). 7.4.4 Applications of seismic hazard assessment. Seismic hazard assessment plays a vital role in various aspects of earthquake engineering and risk management. The primary applications include 1. Design and construction of earthquake-resistant structures. Seismic hazard assessments inform the design parameters of earthquake-resistant buildings and infrastructure by understanding the expected ground shaking. Engineers can design structures with appropriate strength, flexibility, and damping to withstand seismic forces. 2. Zoning and land use planning. Local governments use seismic hazard assessments to define building codes, land use regulations, and zoning maps. High-risk areas may have stricter construction standards, while areas with lower seismic hazards may have less stringent requirements. 3. Retrofitting existing infrastructure. For existing structures in earthquake-prone areas, seismic hazard assessments help identify the need for retrofitting or strengthening. By understanding the potential seismic risks, engineers can enhance the resilience of buildings, bridges, and other critical infrastructure. 4. Insurance and risk mitigation. Seismic hazard assessments are integral to the insurance industry, helping assess earthquake risk and determine appropriate premiums. These assessments also support government agencies and organizations in developing risk mitigation strategies, including emergency response plans and early warning systems. 5. Emergency preparedness and response. Seismic hazard assessments are used to inform emergency preparedness strategies, including evacuation plans, disaster response plans, and the allocation of resources. By understanding the risks, local authorities can better prepare for the aftermath of a major earthquake. 7.4.5 Conclusion. Ground motion and seismic hazard assessment are fundamental components of geotechnical earthquake engineering. By analyzing the characteristics of ground motion and assessing the seismic hazard at a site, engineers can design structures that are better equipped to withstand the forces generated by earthquakes. These assessments play a key role in earthquake-resistant design, land use planning, retrofitting, and emergency preparedness, ultimately contributing to the safety and resilience of communities in earthquake-prone regions. Understanding and quantifying seismic hazard allows for informed decision-making and risk reduction strategies that can save lives and minimize economic loss during seismic events. Chapter 7: Geotechnical Earthquake Engineering. 7.5 Earthquake-induced ground movements and their EX. Earthquake-induced ground movements are a critical concern in geotechnical earthquake engineering, as they directly influence the stability and performance of structures, foundations, and infrastructure during and after seismic events. These movements result from the propagation of seismic waves through the Earth's crust and can cause various types of ground deformations, including displacements, settlement, and liquefaction. Understanding these movements and their EX is essential for the design of safe and resilient structures in earthquake-prone regions. This section explores the types of earthquake-induced ground movements, their causes, and their EX on geotechnical engineering projects. It also discusses the methods used to assess and mitigate these movements in the context of earthquake-resistant design. 7.5.1 Types of earthquake-induced ground movements. The ground can experience a variety of movements during an earthquake, depending on factors such as seismic wave propagation, local soil conditions, and topography. These movements include 1. Horizontal ground displacement. Horizontal displacements occur due to the movement of seismic waves that cause the ground to shift laterally. This can ECT surface features such as roads, pipelines, and buildings, particularly those that are poorly anchored or not designed to withstand horizontal forces. Strike-slip faulting. This type of displacement occurs along vertical faults, where there is lateral horizontal movement. The ground on either side of the fault moves horizontally, which can cause displacement of structures and infrastructure. 2. Vertical ground displacement. Vertical displacements result from seismic waves causing the ground to move up or down. These displacements can lead to the settlement or uplift of structures, depending on the direction of motion. Vertical ground movement can also ECT the alignment of structures and utilities. Thrust faulting. Vertical displacement is typically associated with thrust faulting, where one block of the Earth's crust is pushed upward over the other. 3. Surface rupture. Surface rupture occurs when fault lines on the Earth's surface break during an earthquake, displacing the ground along the fault trace. This type of ground movement can lead to significant damage to structures, roads, and pipelines crossing the fault line. Surface rupture is often the most direct and visible result of an earthquake. 4. Seismic settlement. Seismic settlement refers to the downward displacement of the ground during an earthquake caused by the compaction or consolidation of loose, granular soils or soft clays. This phenomenon can lead to the settling of buildings, roads, and other infrastructure. Seismic settlement is more pronounced in soft, loose, or saturated soils, which are prone to compression during strong ground shaking. 5. Liquefaction-induced ground movement. Liquefaction occurs when saturated, loose sandy soils lose their strength and behave like a fluid due to strong seismic shaking. This phenomenon can result in significant ground displacement, where structures may tilt, sink, or float, and can lead to the formation of sand boils or fissures. Liquefaction is most likely to occur in shallow, water-saturated soils, often in areas with a high groundwater table. 6. Landslides and slope failure. Earthquakes can trigger landslides and slope failures, particularly in areas with steep terrain or loose, unconsolidated materials. Seismic shaking can cause the soil on slopes to lose its stability, leading to landslides that displace large amounts of soil and rock. Landslides can result in property damage, road closures, and significant disruption to infrastructure. 7. Soil amplification. Soil amplification refers to the increase in the intensity of ground shaking at the surface due to the characteristics of the underlying soil. Soft soils amplify seismic waves, leading to higher ground motion at the surface than at deeper levels. This EECT can lead to greater displacement and deformation in structures located on such soils. 7.5.2 EX of earthquake-induced ground movements on structures. The EX of earthquake-induced ground movements can vary widely depending on the nature of the ground movement, the type of structure, and the local site conditions. These EX include 1. Foundation displacement and settlement. Foundations are particularly vulnerable to earthquake-induced ground movements, as horizontal and vertical displacements can lead to the tilting, sinking, or shifting of structures. In soft or poorly compacted soils, seismic settlement can cause differential settlement, leading to cracking, tilting, or even collapse of buildings. Foundations on granular soils or saturated sand layers are at a higher risk of experiencing liquefaction-induced settlement. 2. Structural damage. Structures may be subjected to various forms of damage, such as cracking, buckling, and failure due to horizontal and vertical ground movements. The severity of the damage depends on the type of structure, its design, and the amount of displacement it experiences. Buildings, bridges, and other infrastructure may suffer from damage such as foundation cracking and displacement, pounding between buildings in dense urban areas, beam and column failure, structural misalignment. Structures designed without adequate consideration of seismic ground movement can be severely compromised during an earthquake. 3. Pipeline and utility disruptions. Earthquake-induced ground movements can cause pipelines, sewers, and other utility lines to rupture or displace. Horizontal ground displacements, in particular, can lead to significant deformation or breakage of pipelines. In Areas prone to surface rupture or liquefaction, utilities may be cut or damaged, leading to extended outages and disruptions. The displacement of utilities can also cause secondary hazards such as fires, flooding, and loss of water supply, which may complicate emergency response efforts. 4. Landslides and ground shifts. Landslides can bury infrastructure, cause road closures, and displace structures. In regions with steep slopes or poor soil conditions, seismic shaking may trigger landslides that result in substantial movement of large volumes of soil and rock. The effects of landslides are often severe, as they can bury buildings, roads, and utilities and lead to the complete loss of infrastructure in the affected area. 5. Soil liquefaction. Liquefaction-induced ground movements can lead to a dramatic loss of soil strength, resulting in the sinking, tilting, or floating of structures. Structures may experience severe tilting or settlement, and in extreme cases, they may collapse or be displaced horizontally. Additionally, the formation of sand boils or surface cracks can create surface hazards, further compromising the safety of structures. 7.5.3 Assessing earthquake-induced ground movements. To mitigate the effects of earthquake-induced ground movements, it is crucial to assess the potential for ground displacement during seismic events. Several methods and approaches are used to evaluate these movements. 1. Site-specific ground motion analysis. Conducting seismic site response analysis helps in determining the expected ground shaking at a particular location. This analysis considers local soil properties, bedrock conditions, and seismic wave characteristics. Site response analysis is essential in identifying areas where amplification or settlement is likely to occur. 2. Liquefaction potential evaluation. Engineers assess the liquefaction potential of soils through a variety of methods, including laboratory testing, field sampling, and dynamic analysis. The evaluation includes determining factors such as soil type, density, and groundwater levels, which influence the likelihood of liquefaction. Liquefaction-induced ground displacement can be mitigated through soil improvement techniques like densification or grouting. 3. Slope stability analysis. For areas with steep slopes, a detailed slope stability analysis is performed to assess the potential for landslides. This analysis considers factors such as soil composition, slope geometry, and groundwater conditions to predict how seismic shaking may affect the stability of the slope. Remediation strategies like slope reinforcement, retaining walls, and drainage systems may be used to prevent slope failure. 4. Surface rupture and fault displacement analysis. Surface rupture analysis helps identify active fault lines and assess the risk of fault displacement during an earthquake. Geophysical surveys, fault trace mapping, and historical earthquake data are used to predict potential surface rupture zones. In areas of high risk, avoidance or reinforcement of structures crossing fault zones is recommended. 7.5.4 Mitigation measures for earthquake-induced ground movements. Several engineering practices and techniques can help mitigate the effects of earthquake-induced ground movements on structures and infrastructure. 1. Soil improvement. Soil stabilization methods, such as compaction, grouting, and ground freezing, can improve the strength and resistance of soils to seismic settlement and liquefaction. Reinforcing soft or loose soils can significantly reduce the risk of ground displacement. 2. Foundation design. Seismic-resistant foundations are critical for structures in earthquake-prone areas. Deep foundations, such as piles and drilled shafts, can anchor structures to stable bedrock, preventing settlement or tilting. Additionally, base isolation techniques, where flexible bearings are used between the foundation and the superstructure, can absorb seismic energy and reduce the impact of ground motion on buildings. 3. Retaining walls and slope reinforcement. To prevent landslides and slope failure, retaining walls, soil nails, and geotextile reinforcements can be used to stabilize slopes. Proper drainage systems are also essential to reduce poor water pressure and enhance soil stability during seismic events. 4. Flexible infrastructure. For pipelines and utility networks, flexible joints and reinforced materials can reduce the risk of rupture during horizontal ground movements, ensuring that utilities are designed to withstand ground shifts and are placed in less susceptible areas can also help reduce the risk of damage. 5. Zoning and land use planning. Avoiding construction on or near active fault zones, liquefaction-prone areas, or steep slopes can significantly reduce the risk of damage from earthquake-induced ground movements. Zoning laws and building codes should reflect seismic risk assessments and include provisions for reinforcing structures in high-risk areas. 7.5.5 Conclusion. Earthquake-induced ground movements, including horizontal and vertical displacement, liquefaction, and landslides, can cause significant damage to infrastructure, buildings, and utilities. Understanding the nature and potential effects of these movements is essential for designing and constructing earthquake-resistant structures. By employing advanced site assessment techniques, structural design modifications, and mitigation measures, the risks posed by earthquake-induced ground movements can be minimized, contributing to the safety and resilience of communities in seismic regions. Chapter 7. Geotechnical Earthquake Engineering. 7.6 Design of foundations under seismic loading. The design of foundations under seismic loading is a critical aspect of geotechnical. Earthquake engineering. Earthquakes generate dynamic forces that at ECT both the superstructure and the foundation of buildings and infrastructure. A well-designed foundation must not only support the static loads from the structure, but also be able to resist the additional forces induced by seismic activity. Failure to adequately design foundations for seismic conditions can result in catastrophic damage, even if the structure itself is otherwise robust. This section discusses the principles, methods, and considerations involved in the design of foundations to withstand seismic loading. It covers key topics such as the behavior of soils during an earthquake, the impact of seismic forces on foundations, and various design strategies to ensure foundation stability and safety during seismic events. 7.6.1 Seismic loading and its impact on foundations. Seismic loading refers to the dynamic forces exerted on a structure and its foundation due to ground motion during an earthquake. The nature of seismic loading depends on several factors, including the magnitude and duration of the earthquake, the characteristics of the seismic waves, the distance from the earthquake's epicenter, and the local soil conditions. Key factors affecting seismic loading on foundations include 1. Dynamic soil behavior. During an earthquake, soil behaves differently than under static conditions. The ground can experience horizontal and vertical displacements, liquefaction, or settlement, all of which are ECT foundation performance. The soil shear strength and compressibility are critical to understanding how it will behave under seismic loading. 2. Peak ground acceleration (PGA). The peak ground acceleration is a primary measure of the intensity of seismic shaking. It defines the maximum rate of acceleration experienced by the ground surface. Higher PGA values increase the seismic forces acting on a foundation, particularly in soft or loose soils that may undergo significant displacement. 3. Foundation steepness and dynamic interaction. The interaction between the foundation and the soil during an earthquake is essential to understanding how forces are transmitted through the system. Foundations that are too steep may amplify seismic forces, while excessively flexible foundations may undergo excessive movement, leading to structural damage. The foundation must be designed to balance steepness and flexibility to minimize the effects of seismic loading. 7.6.2 Types of foundations under seismic loading. The design of foundations under seismic loading varies based on the type of foundation and its interaction with the underlying soil. There are two main types of foundations typically used in earthquake-resistant design. 1. Shallow foundations. Shallow foundations, including spread footings, mat foundations, and slab, On-grade foundations are placed near the surface of the soil. These foundations are commonly used for light to medium structures. Challenges: in earthquake-prone areas, shallow foundations can be susceptible to differential settlement, tilting, or uplifting due to horizontal ground displacements, liquefaction, or soil failure. Their design needs to account for potential soil displacement and ensure stability during seismic events. Seismic considerations: the design must include an analysis of the soil's response to seismic forces, including possible liquefaction, ground settlement, and horizontal displacement. In some cases, the foundation may need to be designed with deeper elements or reinforced to prevent failure. 2. Deep foundations, piles, and drilled shafts. Deep foundations are often used when shallow foundations cannot provide sufficient stability or when soil conditions are unfavorable. Piles, drilled shafts, and caissons are common deep foundation types. Challenges: deep foundations are particularly critical in areas where the soil near the surface is weak or prone to liquefaction. Piles must be anchored into deeper, more stable layers of soil or bedrock to resist the additional seismic forces. Seismic considerations: the foundation design must consider the lateral and axial forces induced by seismic activity. Piles are designed to resist the lateral motion caused by horizontal ground displacement, and their flexural strength must be sufficient to withstand bending during the earthquake. 7.6.3 Seismic design considerations for foundations. Several key factors need to be considered when designing foundations under seismic loading. 1. Soil structure interaction. Soil structure interaction, SSI, refers to the mutual influence between the foundation and the surrounding soil during an earthquake. This interaction can amplify or dampen seismic forces depending on factors such as the type of soil, foundation steepness, and the dynamic properties of the structure. SSI is an important consideration in the design of both shallow and deep foundations. Methods for SSI analysis. Linear elastic methods for simple analysis of soil structure. Interaction. Nonlinear dynamic methods for more complex assessments, particularly for sites with soft or liquefiable soils. Use of finite element analysis, FEA, and boundary element methods, BM, for detailed simulations of the seismic response of the foundation and soil system. 2. Foundation flexibility and damping. Foundations must be designed to have a level of flexibility that allows them to absorb and dissipate seismic energy. This can be achieved by including materials or design elements that introduce damping, such as base isolators or flexible joints. The goal is to prevent excessive vibrations and avoid resonant frequencies that could amplify seismic forces. Base isolation. One effective technique for mitigating seismic loading is the use of base isolators, which decouple the building from the ground motion, allowing the structure to move independently of the seismic forces acting on the foundation. 3. Liquefaction resistance. Liquefaction occurs when saturated soils lose their strength and behave like a liquid during seismic shaking. In areas prone to liquefaction, foundations must be designed to withstand the potential loss of soil strength and settlement. Mitigation measures. Use of deep foundations that penetrate below the liquefiable layers to reach more stable soils. Soil improvement techniques such as vibrocompaction, grouting, and dynamic compaction to increase the density and resistance of soils to liquefaction. 4. Seismic settlement and differential settlement. Seismic settlement occurs when loose or soft soils undergo compression during ground shaking. Differential settlement, where different parts of a foundation settle unevenly, can cause tilting or cracking of the structure. Design solutions. To mitigate these effects, foundations may be designed to distribute loads evenly across the soil, such as through mat foundations or reinforced slab designs. If soil improvement is not feasible, deep foundations may be required to bypass weak layers and transfer loads to more stable soil or bedrock. 5. Ground shaking and lateral forces. The horizontal forces generated by ground shaking can cause lateral displacement of foundations, particularly those with shallow depths. These forces may result in sliding or tilting of the foundation, particularly if the soil is loose or poorly compacted. Lateral force resistance. To resist lateral forces, foundations may incorporate shear keys, tie beams, or lateral piles to resist horizontal movement. Additionally, the foundation's design must ensure that the building structure itself is designed to resist these lateral forces through shear walls or braced frames. 7.6.4 Design approaches and methods. Several approaches and methods can be used to design foundations under seismic loading. 1. Seismic code requirements. Design codes such as the International Building Code, IBC, Eurocode 8, and ASC 7 provide guidelines for designing foundations under seismic loading. These codes consider factors such as seismic hazard assessment, site conditions, and expected ground shaking to determine the necessary design parameters for foundations. Factor of safety. A factor of safety, FOS, is often incorporated into the design to account for uncertainties in soil properties and seismic forces. FOS values vary depending on the type of foundation, soil conditions, and level of seismic hazard. 2. Equivalent static method. The equivalent static method is a simplified approach used in some cases to estimate the seismic forces acting on a foundation. This method applies a static force proportional to the weight of the structure, and the force is then distributed to the foundation based on its steepness. While this method is not suitable for all scenarios, it is often used in preliminary design stages for smaller structures or areas with moderate seismic risk. 3. Dynamic analysis and response spectra. Dynamic analysis is used to evaluate the foundation's response to seismic loading. This involves using response spectra to calculate the peak seismic forces on the foundation based on the dynamic properties of the soil and structure. The analysis considers both horizontal and vertical components of seismic loading. Time history analysis. For more detailed evaluation, time history analysis can be used to model the ground motion as it changes over time and evaluate the foundation's response to real earthquake records. 7.6.5 Mitigation strategies for foundations under seismic loading. To reduce the impact of seismic loading on foundations, several mitigation strategies can be employed. 1. Base isolation. Base isolators can decouple the foundation from seismic forces, allowing the superstructure to move independently from the ground motion. This reduces the stresses on the foundation and prevents excessive damage. 2. Soil improvement techniques. Techniques such as grouting, compaction, or the addition of reinforcing materials, geotextiles, geogrids, can improve soil strength and resistance to liquefaction, settlement, and other earthquake-induced deformations. 3. Reinforced foundations. Foundations can be reinforced with steel or concrete elements to increase their load-bearing capacity and resistance to lateral forces. Reinforced mat. Foundations or pile caps are commonly used in areas with high seismic risk. 4. Monitoring and maintenance. After an earthquake, the foundation should be inspected and monitored for signs of settlement, cracking, or displacement. Regular maintenance and reinforcement of foundations can ensure long-term performance in seismic conditions. 7.6.6 Conclusion. Designing foundations to withstand seismic loading requires a comprehensive understanding of soil behavior during earthquakes and the dynamic interaction between the foundation and the surrounding soil. By considering factors such as soil structure, interaction, liquefaction potential, and lateral forces, engineers can develop foundation designs that minimize the risk of damage during seismic events. The use of modern analysis methods, foundation reinforcement techniques, and mitigation strategies ensures that foundations remain stable and effective, even in the most challenging seismic environments. We hope you found the content informative and valuable. The link to next part of this video will be embedded in the description below, so be sure to check it out. If you enjoyed the video, please click like and share it with others. And if you haven't subscribed to our channel yet, make sure to hit the subscribe button now so you don't miss out on future content.